Welcome to this video on sequential logic. Here we will cover what is sequential logic and why is it needed for computer memory. What is a flip-flop? How does a flip-flop work? Why the flip-flop is the answer to our question of computer memory, and how to design a counter circuit using memory. Understanding sequential logic gives you many more skills to design digital logic circuits and is an important progression from combinational logic. If you haven't checked out our previous videos, make sure to do this if you get stuck. To begin to understand sequential logic, you need to begin with this diagram. The overall idea is that you have present states that are at the input and next states are at the output. The next state is determined by the present state and what states have come before in order to make a decision. Combinational logic is used alongside our memory to deliver this function. Computers need this to be able to decide what will happen next. For example, if you want to design a counter with a display, the computer needs to move to the next state in the correct order to count upwards. But it needs to remember what has already been so that it can trigger the correct segments of the display at the right time. We will return to this later. First, the flip-flop must be introduced. Here is a flip-flop. It contains logic gates we have already seen, the NOR gate. S stands for set and R stands for reset. The output, X, determines what is next alongside the inputs. Let's consider some inputs to explain. If we say that X is 0 initially, then X bar is 1. If 0, 0 is input, then by simply considering each NOR gate, the outputs become 1, 0, as shown. These have not changed, so 0, 0 doesn't change anything. So it's called hold. Now let's consider changing the inputs so that S is equal to 1. Initially, we use the same conditions so that X bar starts out as 1 and X is 0. When S changes to a 1, the top NOR gate changes to a 0, which changes the input to the bottom NOR gate, which in turn changes the output to a 1. Hence, X is now a 1. This is the set condition. There are other behaviors that need to be accounted for, but by using the same idea of the changes propagating through the circuit, you can see how the hold, set, and reset conditions work. Regardless of present state, set makes X equal to 1, reset makes X equal to 0, and hold will keep the present state the same. There is a condition to be careful with. This is when the inputs are 1, 1. The problem is that it is ambiguous what changes happen first. But you can't have a condition where X and X bar are the same, as they are always different. There are some flip-flops that may allow for a toggle condition, but in general, this input is not allowed. Now that you understand how the flip-flop works, it is important to sequential logic design to consider the state diagram. Here, you can see that there are two states, X output of 1 and X output of 0. The arrows show transitions, and inputs are shown above the arrows. In this case, the only inputs are S and R. We write them side by side as shown. By comparing this to the table on the previous slide, you can see how all inputs are accounted for, showing why transitions occur. This diagram is for a latch, but the difference between this and a flip-flop is that flip-flops change on a clock pulse rising or falling edge, which is used to synchronize changes. You should now be able to see that the simplest form of memory has been made with this circuit. The ability to remember the previous state before it is rewritten is the fundamental idea of volatile memory. Whilst computer memory is more complex and requires more understanding of computer architecture, this is the core knowledge you need. Now for the example design task. Consider designing a circuit that counts upwards from 0 to 3 when a button is pressed to keep a score. We need 4 numbers to be represented by binary signals. As we need 4 numbers, log base 2 of 4 is 2, so 2 bits are needed. This is represented in binary as shown, compared with decimal system. To proceed, a state diagram is needed. We need 4 states. Each state will trigger combinational logic for the display to represent the numbers. If we consider going around the diagram, we start at A, which is represented by 0, 0, and count upwards to D, which is represented by 1, 1. Each button press will change B to a 1 so that the score is increased by 1. When a button is not pressed, B is 0, so we have to remain in the present state. The next state transition table will help with further analysis. Here, we have assigned state codes so that the states represent the numbers that also need outputting. You can see how we have the necessary transitions from the present state in the first column to the next state in the second column when B is 0 and 1 respectively. We also require 2 bits for the output to represent each number output. Although we won't go further into what happens to the outputs, further logic would be required to connect it to the displays. Karnaugh maps are needed to track the bit changes to find the logic to implement. We need logic between the output of the flip-flops, which feed back into the inputs, and logic incorporating the input B into the decision to move between states. Here we are using only 2 bits, so we need 2 flip-flops. One flip-flop will control how the first bit of the present state changes to either of the first bits of the next state, as shown by the color coding. In order to design, we need to select the flip-flop technology to use. Here we will use a D-type flip-flop. All this does is require a single input, D, which has logic that covers both S and R inputs, so it is no different in function. It is just simpler to have only a single input. You can see the behavior as written, so when D is 1, it acts as a set condition, and when D is 0, it acts as a reset condition. The Karnaugh maps are used to find the logic between the outputs of the flip-flops, W and Z, and the input B to make the D input change the state when necessary. For example, with the first Karnaugh map, when W and Z equals 0, 0 and B equals 0, we require the state to stay the same, so D needs to be 0 to ensure that the W output won't change, as shown in the top left corner of the map. The reason why it is 0 is because that is what the D input needs to be to stay as a 0 for this flip-flop technology. This can be a complex process to follow, so make sure to stop the video and compare the table to the Karnaugh maps. Once all is complete, you can loop ones in the Karnaugh maps to find the logic required. The diagrams follow from here. This behavior will represent a score counter that counts upwards from 0 to 3, then back to 0 if it gets higher than 3. To display this on a screen, you would need logic from the outputs of the flip-flops to achieve this. Here, you can see the Boolean expressions along with the circuit diagram for this circuit. The flip-flops are shown on the right-hand side with outputs W and Z used to represent states and count upwards. The left-hand side shows the combinational logic derived from the Karnaugh maps to influence the D input to change the state according to the button press B. Although this diagram looks complicated, it is the most simple logic we can use to implement this function. Please subscribe to support this channel and check out our other videos on digital electronics and circuit analysis. For a comprehensive overview of the direction of progression of our videos, check out the map of electronics.